In this video, we introduce even and odd functions. This is sometimes called function parity. So we're going to define even and odd functions algebraically. Then we're going to show how it leads to symmetries in their graphs. And finally, we end with a couple examples of algebraically verifying the parity of a function and then producing a graph to show that it has the correct symmetry. So we start with even functions. And a function is even if it has this property, that f of negative x is equal to f of x. So I produced a plot of such a function below, and it should help to explain what the algebra actually means. So suppose I look at a location x right here. Well, f of x is just the y-coordinate connected to that x value, so there's f of x. And if I go to negative x, that's over here in equal distance from the origin. And I can see I get the same y value connected to that. In other words, f of negative x is the same y value as f of x. So that's how that little formula corresponds to the symmetry in the graph. And we would call this symmetric about the y-axis. It's as if one half of the function is simply reflected through a mirror on the y-axis. So how do we apply this algebraic definition? In the example, we're asked to show that f of x equals x squared is even. This is actually where the word even comes from. If you have a power function with an even exponent, it does turn out to be even. And then we're going to plot it to make sure it has the correct symmetry. So here's how we test the parity of f. I look at f of negative x. Simply replace x with negative x, and then simplify when I square this thing, just to really draw it out so it's clear how the algebra works. I have a negative times negative, which is a positive, and I just get x squared. Well, that's the original function f of x. So I just showed that f of negative x is equal to f of x, and our function is even. Now let's look at a plot of this thing. So there's the graph of f of x, and there's no surprises here. This is the simplest parabola, a very familiar curve, and I see that it does indeed have the symmetry around the y-axis. All right, let's look at odd functions. So a function is odd if it has the property that f of negative x is equal to the negative of f of x. The symmetry this produces I referred to as a rotational symmetry about the origin. In other words, if I view the origin as a rotation axis, I could spin the graph by 180 degrees and it would just produce a copy of the original graph. This, by the way, is totally equivalent to reflecting the graph over the y-axis and then reflecting it over the x-axis if you would prefer to think about it that way. So let's look at how this algebraic property produces this symmetry. I'm just going to look at some value of x here. And of course, f of x is the y-coordinate connected to that x by the graph. And there it is. And if I go to the same distance to the left of the origin, the x value there is negative x. And I can see because of this rotational symmetry, my y-coordinate has exactly the same magnitude, but the opposite sign. So f of negative x and f of x are opposites. So I can say f of negative x is the negative of f of x. In our example, we're asked to show that f of x equals x cubed is odd. And again, the words even and odd come from this idea that for a power function, if the exponent is an even number, it's an even function. If the exponent is an odd number, it's an odd function. But you should know there are all sorts of other functions that are even and odd that are not power functions. So we're using the words even and odd to refer to this special symmetry and these special algebraic properties, not the actual even and odd numbers. We do the proof in the standard way. Evaluate f of negative x. I'll do a little different style this time. I'm going to go ahead and write that minus sign as a -1. Again, this is a little bit long and drawn out compared to what you really have to show, but I wanted to be clear. And -1 cubed is -1. So I end up with a minus sign in front of this. Well, negative x cubed is the negative of my original function, f of x. So I have f of negative x equals negative f of x, and we've proven that this function is odd. Let's take a look at the graph to make sure it has the right symmetry. Okay, so there's the graph of f of x equals x cubed, and I can see it does indeed have rotational symmetry of 180 degrees about the origin. If you find the math content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce dozens of new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.